Picture a cosmic engine so powerful it can outshine an entire galaxy. A single point of light burning brighter than 100 billion stars. This isn't science fiction. It's a quasar, one of the most violent and mysterious objects in the universe. These dazzling monsters, lurking in the darkest corners of space, aren't just rare oddities. They're the universe's way of showing off, blasting out energy like a cosmic fireworks display that never ends. But what exactly are these celestial powerhouses, and what's fueling their impossible brilliance? That's the mystery we're about to unravel. Quasars and their cousins, active galactic nuclei or AGNs, are like the universe's ultimate energy factories. Think of them as cosmic dragons, hoarding unimaginable power at the centers of galaxies, devouring everything that strays too close. Their light has traveled across billions of years just to reach us, carrying secrets from a time when the universe was young and wild. Some quasars are so bright they eclipse their own galaxies, turning what should be a bustling metropolis of stars into a faint afterthought. And here's the wildest part. We now know these beasts are powered by supermassive black holes, but that only raises more questions. How can something so dark create light so intense? What happens inside these swirling maelstroms of energy? That's where things get even stranger. Quasars don't just sit there glowing, they spit out jets of superheated plasma longer than entire galaxies. They flicker unpredictably like a cosmic strobe light, and some even seem to defy the laws of physics as we know them. Over the next few moments, we'll dive deep into their bizarre behaviors, from their mind-bending brightness to the way they warp space-time itself. By the time we're done, you'll see why these cosmic monsters have left scientists both awestruck and utterly baffled for decades. So buckle up, we're about to journey into the heart of one of the universe's greatest mysteries. Scientists once thought there was an unbreakable ceiling to how bright an object in space could be, a cosmic speed limit for radiation called the Eddington limit. The math was clear. If a black hole's feeding frenzy got too intense, the sheer pressure of its own radiation should blast away the surrounding gas, cutting off its fuel supply like a fuse box tripping from overload. But quasars laugh in the face of limits. Some blaze with such ferocious intensity that they outright shatter this theoretical boundary, pumping out enough energy to rip themselves apart. And yet, there they are, burning defiantly against all expectations. So how do they cheat physics? One possibility is that these quasars are gorging themselves beyond reason in a state called super-Eddington accretion. Picture a black hole not just sipping on its surroundings but gulping down matter faster than the radiation can push back, like trying to blow out a bonfire with a hurricane wind fanning the flames. The infalling gas gets compressed into a swirling, chaotic maelstrom, creating conditions so extreme that even our best simulations struggle to replicate them. Some theorists suggest magnetic fields might act like cosmic rains, channeling the chaos and keeping the feast going far past what should be possible. Then there's the jet scenario. If a quasar's radiation isn't blasting outward in all directions but gets funneled into narrow, superheated beams, think of a lighthouse beam versus a light bulb, the numbers suddenly make sense. From certain angles, we'd see an illusion of impossible brightness, like staring down the barrel of a cosmic blowtorch. But even this explanation leaves gaps. Some quasars flicker in brightness over mere days, implying their energy factories are smaller than our solar system. How can something so tiny defy a law that should apply to all black holes? The truth might be messier and more thrilling than we imagined. Perhaps these outliers aren't just breaking the rules, they're revealing flaws in our textbooks. What if the Eddington limit isn't absolute, but more like a guideline that collapses under extreme conditions? Every time we find another of these radiant rebels, it chips away at our assumptions, forcing us to rewrite the laws of black hole thermodynamics. After all, the universe has never been one to play by the rules. If quasars are the universe's most violent power plants, their ultra-fast outflows are the hurricane-force winds they blast into the cosmos. Picture this: a supermassive black hole doesn't just devour matter. It spits some back out with such fury that these cosmic gusts rip through space at 20 to 30% the speed of light. That's like a storm racing from Earth to the Moon in less than 5 seconds. These aren't gentle breezes, they're tsunamis of charged particles, hot enough to tear through gas clouds and reshape entire galaxies. What makes these outflows truly bizarre is their sheer force. They carry enough energy to punch holes in their host galaxies, heating up interstellar gas so intensely that new stars can't form. It's like a cosmic feedback loop. The black hole's appetite fuels its own fury, which then starves future generations of stars. Some outflows stretch for hundreds of thousands of light years, splattering across intergalactic space like paint from a high-pressure hose. But here's the real mystery. How can gravity's ultimate trap, a black hole, launch material outward at such insane speeds? The leading theory involves magnetic fields twisted into cosmic slingshots, flinging matter away before it crosses the event horizon. Others suggest the outflows are like pressure valves, releasing excess energy from the frenzied whirlpool of gas spiraling inward. Either way, these winds are more than just spectacular. They're proof that black holes don't just lurk in the darkness. They reach out and sculpt the universe around them. The most mind-bending part, we're seeing these outflows in action across billions of years. A quasar's outflow might have begun its journey when Earth was just molten rock, and its light is only reaching us now. That means we're watching ancient fireworks, the last echoes of violence that shaped galaxies eons before our sun even ignited. And if that doesn't make you feel small, nothing will. Some quasars don't just speak in light, they stutter. When astronomers train their telescopes on these cosmic beacons, they occasionally catch something strange. Emission lines in their spectra split into twin peaks like a ghostly echo of themselves. These aren't random blips, they're clues etched into the fabric of space-time, hinting at structures or events so extreme they defy simple explanation. The leading theory points to a whirling disk of superheated gas spiraling into the black hole at nearly light speed. Picture a record spinning so fast its edges blur, except this disk is millions of miles wide, and its rotation stretches the very light it emits. As one side races toward us, its light gets squeezed into shorter, bluer wavelengths, while the fleeing side stretches light redder. The result, a spectral double peak, the fingerprint of a cosmic carousel spinning at the edge of oblivion. But there's a twist. Some double-peaked lines don't match the clean symmetry of a single disk. They're lopsided, erratic, as if two colossal engines are clashing in the dark. This raises a tantalizing possibility. What if we're seeing not one black hole feeding, but two supermassive binary black holes locked in a gravitational waltz, each dragging its own glowing disk of doomed matter? The math checks out when galaxies collide. Their central black holes should spiral together, creating a temporary dance of destruction before merging. Yet not everyone's convinced. Critics argue these double peaks could come from turbulent bubbles in a single disk, or even relativistic jets punching through gas clouds. The debate gets heated because the stakes are cosmic. If these are truly binary black holes, they'd be the ultimate testbed for Einstein's theories, warping space-time so severely they'd ripple the universe with gravitational waves. Every flicker in these spectral lines carries weight. A matched double peak might reveal the spin of a black hole's accretion disk, while an uneven split could betray the presence of an invisible companion. It's like listening to a cosmic heartbeat, except the heart is a monster, and every irregular pulse rewrites what we know about how black holes grow, collide, and shape the galaxies around them. So why haven't we solved this yet? Blame the sheer distance. Even our sharpest telescopes struggle to untangle the details of quasars billions of light years away. Each observation is like studying a lighthouse through a sandstorm. We catch glimpses, but the full picture stays maddeningly out of focus. Until we peer deeper, these double-peaked enigmas will keep us guessing, reminding us that the universe always has another card up its sleeve. Just when astronomers thought they had quasars figured out, the universe threw them another curveball, changing-look quasars, celestial chameleons that flip their personality overnight. Imagine watching a lighthouse suddenly dim from blinding brilliance to a faint flicker, not over centuries or even years, but mere months. That's exactly what these shape-shifting enigmas do, rewriting their own spectra as if flipping a cosmic switch. What makes these transformations so baffling is that quasars were long considered the steadiest monsters in the cosmos, reliable beacons burning with near-constant ferocity. But in 2007, astronomers caught one red-handed. A quasar in the constellation Cetus faded by a factor of 7 in just 6 years, its broad emission lines, the telltale fingerprints of a supermassive black hole's feeding frenzy, vanishing like a snuffed candle. Since then, dozens more have been caught mid-metamorphosis, some swinging between spectral types as dramatically as flipping from a roaring bonfire to glowing embers and back again. So what's behind this cosmic moodiness? One leading suspect is the accretion disk itself, that swirling platter of doomed gas orbiting the black hole. Turbulence or magnetic instabilities might cause sections to heat up or cool abruptly, like a stovetop burner flickering between high and low. In this scenario, the quasar isn't truly changing, we're just seeing its dinner plate sputter under extreme conditions. But there's a wilder possibility. Some researchers argue thick clouds of dust larger than our solar system could be drifting across our line of sight, acting like cosmic Venetian blinds. One moment we see the quasar's full glory, the next a passing dust storm muffles its light. The craziest part, these obscuring clouds wouldn't just dim the view, they'd selectively block certain wavelengths, altering the quasar's apparent spectral type entirely. Then there's the most dramatic explanation of all. The black hole might be gorging itself in fits and starts. Picture a starving beast suddenly finding a fresh cache of gas. The influx would spike its brightness until the meal runs thin, causing a rapid fade. Repeat the cycle, and you've got a quasar that flickers like a faulty neon sign. Supporting this, some changing-look quasars show evidence of recent tidal disruption events. The violent shredding of a star that wandered too close, providing a temporary feast. Yet every theory has holes. If obscuring clouds are to blame, why don't all quasars show these changes? And how could disk instabilities explain shifts happening faster than gas can physically spiral inward? The answers might rewrite our understanding of how black holes feed. Some astronomers now suspect we're seeing multiple mechanisms at play, like a cosmic orchestra where different instruments take turns driving the melody. What's undeniable is that these shape-shifters prove one thing: quasars are anything but predictable. They remind us that even the universe's most titanic structures can pivot on a dime, keeping astronomers perpetually on their toes. After all, when you're dealing with monsters that bend the laws of physics, expecting them to play by the rules was our first mistake. Quasars are supposed to have a home, a sprawling galaxy swirling around them like a cosmic nest. But in recent years, astronomers have stumbled upon something that shouldn't exist: quasars floating in the void like lighthouse beams with no island beneath them. These apparent loners defy everything we know about how supermassive black holes form, because without a galaxy to feed them, how do they grow so bright? The answer might rewrite the rules of black hole evolution, or reveal something even stranger happening in the dark. Take the case of He 0450-2958, a quasar 720 million light-years away that seemed to have no galaxy at all. When researchers pointed the Hubble Space Telescope at it, they expected to see the usual fuzzy glow of stars surrounding the quasar, but the space around it was eerily empty. At first glance, it looked like a rogue black hole blazing through intergalactic space, untethered and alone. But the universe loves playing tricks. deeper observations revealed wisps of gas and dust swirling nearby, tattered remnants of what might have once been a full-fledged galaxy. The leading theory: this quasar didn't lose its home, it destroyed it. The sheer force of its radiation and outflows could have blown away or heated up most of the galaxy's star-forming gas, leaving behind a ghostly wreck too faint to see. Imagine a wildfire so intense it burns away an entire forest, leaving only smoke and embers. That's the kind of violence we might be witnessing here. There's another possibility: cosmic collisions. When two galaxies merge, their supermassive black holes can get flung into the void by gravitational recoil, like a slingshot firing a stone into the dark. These ejected quasars would carry a faint trail of stars and gas, a galactic fingerprint too diffuse for our telescopes to easily spot. Some might even be born in the chaos of galaxy clusters, where gravitational tugs of war can rip a black hole free from its galactic anchor. Yet the plot thickens. A few quasars show no trace of a host, no debris, no hint of destruction, just pure, unsettling isolation. Are they primordial black holes formed in the early universe before galaxies even existed? Or could their light be gravitationally lensed, stretched and magnified by unseen matter until the galaxy behind it fades into invisibility? The truth might be a mix of all these scenarios, proving that even the universe's most predictable monsters have a way of keeping us guessing. What's clear is this: every naked quasar we find forces us to rethink how black holes and galaxies grow together. Maybe some quasars outshine their homes into obscurity, or maybe we're seeing the aftermath of a cosmic demolition job. Either way, these lonely giants remind us that the universe has more tricks up its sleeve than we ever imagined. Einstein would roll over in his grave. Some quasar jets seem to break his ultimate speed limit. When radio telescopes zoom in on these cosmic fire hoses, they sometimes spot bright knots racing outward at mind-bending speeds 5, 7, even 10 times the speed of light. Impossible, absolutely. But the universe loves a good magic trick, and this illusion, called superluminal motion, reveals just how warped reality gets near these gravitational monsters. Here's how the cosmic sleight of hand works. Imagine a quasar's jet pointing almost directly at us, its material screaming through space at 99% light speed. As each new blob of plasma erupts from the core, it follows a path slightly angled toward our line of sight. The first photons from that blob have a shorter distance to travel to reach us than the ones emitted later as the blob moves outward. Our perspective compresses the arrival time, like watching a movie in fast forward. The result: we perceive the blob's sideways motion as impossibly fast, a relativistic mirage. Picture a plane flying low over your head at near sound speed. By the time you hear the sonic boom from its nose, the tail's noise is already reaching you too, collapsing the sound waves into a single thunderclap. Superluminal jets do the same with light, bunching up photons to create an illusion of speed. The closer the jet angles toward us, the more extreme the effect. But this isn't just a cool party trick. It's a goldmine for astrophysics. By measuring these apparent speeds, astronomers can calculate the jet's true velocity and how tightly it's beamed toward us. Some quasars even show reverse motion, where knots appear to backtrack, another perspective trick caused by new ejecta overtaking older material along our line of sight. The wildest implication: these illusions prove jets aren't just streams of hot gas, they're sculpted by forces we're still unraveling. Magnetic fields likely coil them into narrow beams, while the black hole's spin acts like a cosmic drill, twisting space-time itself into an energy channel. Every superluminal knot we spot is a breadcrumb leading back to the engine's inner workings. So while no quasar jet truly breaks light speed, their shadow play teaches us something profound. Near black holes, even light can't be trusted to tell the straight story. And that's the real magic, watching the universe bend its own rules right before our eyes. Redshifts are supposed to be the universe's measuring tape, the stretching of light that tells us how fast an object is fleeing from us as space expands. But some quasars spit in the face of this cosmic rulebook, flashing redshifts that make no sense at all. Take NGC 7603, a spiral galaxy with a quasar seemingly embedded in one of its spiral arms. By all rights, they should share roughly the same redshift since they appear connected. Yet the quasar's light is stretched nearly 4 times more, as if it's racing away much faster than the galaxy it supposedly calls home. This isn't just a fluke. Dozens of quasars defy their surroundings this way, dangling tantalizing possibilities. Maybe redshifts aren't always about cosmic expansion. Some theorists argue these outliers could be emitting light under extreme conditions that warp its wavelengths intrinsically, like a siren whose pitch changes not because the ambulance moves, but because the sound waves ricochet wildly inside the vehicle. Others whisper about unknown physics, perhaps a hidden interaction between light and intergalactic dust, or even flaws in our redshift assumptions. The controversy cuts deep because redshifts anchor our cosmic distance ladder. If they're unreliable for quasars, how much of our universe's map is built on sand? Skeptics point to gravitational lensing or chance alignments. Maybe NGC 7603's quasar isn't truly inside the galaxy but far behind it, its light looping around the galaxy's gravity like a cosmic mirage. Yet even that can't explain all the anomalies. The most radical proposal: these quasars were ejected from their host galaxies at insane speeds, dragging their original redshifts with them like cosmic baggage. Picture a black hole slingshotting away during a galactic collision, its light still carrying the imprint of its birth, but this would require velocities physics barely allows. Every contradictory redshift forces a reckoning. Either our universe holds forces we've yet to imagine, or we're misreading nature's oldest signals. Until we crack this code, these outliers will keep haunting the edges of our cosmic charts, whispering that there's more to the story than we dare admit. Quasars don't just blaze across the cosmos, they leave ghosts behind. Imagine a flare of light so bright it bounces off clouds of interstellar dust like sunlight glinting off a mirror, arriving at Earth years or even decades after the original outburst. These eerie light echoes are the universe's way of hitting rewind, giving us a second chance to witness violent events we missed the first time around. Take the case of Quasar 3C273, where astronomers spotted a brilliant flare in archival data from the 90s, except the quasar itself hadn't flared in decades. The light had taken a detour, ricocheting off a vast dust cloud halfway between the quasar and us. Like hearing an echo in a canyon long after someone shouts, this delayed glow revealed a hidden chapter in the quasar's violent history. Mapping these echoes is like cosmic archaeology. Every dust cloud acts as a celestial film reel, recording snapshots of the quasar's past behavior. By studying the timing and angles of these reflections, astronomers can reconstruct 3D maps of the debris fields surrounding quasars' structures too faint to see directly. Some echoes even hint at ancient eruptions far more powerful than anything we've witnessed in modern observations, suggesting these monsters had even wilder youth. The real magic happens when multiple echoes overlap. Picture a quasar flare from 50 years ago hitting dust clouds at different distances. The light might bounce off a nearby cloud and reach us now, while another reflection from a more distant cloud arrives years later. This creates a time-lapse effect, stretching a single violent moment into a decades-long light show. It's the closest thing we have to a cosmic DVR, but these echoes aren't just pretty relics, they're forensic tools. The way light scatters off dust grains betrays the cloud's composition and structure. Some quasars show reddened echoes where shorter wavelengths get filtered out, proving the presence of certain minerals. Others reveal dust temperatures down to the degree, exposing regions heated by shockwaves from the original blast. The most tantalizing echoes might solve a quasar mystery: why some flicker erratically. If multiple reflections arrive simultaneously, they could mimic chaotic brightness swings, meaning what looks like a quasar throwing tantrums might just be its own past echoing back in chaotic harmony. Every ghostly flare we catch is a window into the unseen architecture around these cosmic monsters, and with new telescopes scanning the skies, we're only beginning to hear the whispers of quasars long gone. The universe, it seems, keeps its own scrapbook, and we're finally learning how to read it. Some of the most violent dances in the universe happen where we can't even see them, in the hearts of quasars, where not one but two supermassive black holes might be locked in a deadly embrace. Picture this: two cosmic titans, each weighing billions of suns, whirling around each other at a fraction of light speed, churning space-time itself into a froth. These binary black hole systems shouldn't just exist, they should be screaming their presence across the cosmos. And yet, catching them in the act has been like trying to spot a pair of fireflies in a hurricane. The best clues come from quirks in quasar light. When astronomers analyze the spectra of certain quasars, they sometimes find emission lines split into two, not cleanly but with a strange, wobbling asymmetry. It's as if the light is being tugged in two directions at once, like a radio signal caught between competing towers. The most likely explanation: two separate accretion disks, each orbiting its own black hole, their light blending into a single, confused fingerprint. Some quasars even show periodic brightness dips, as if something massive is passing in front of the other on a regular schedule, a telltale sign of orbital motion. But confirming these duos isn't easy. At cosmic distances, even a black hole pair separated by the width of our solar system would appear as a single pinprick of light. That's where gravitational waves come in. When these monsters spiral closer, they don't just distort light. They shake the fabric of reality itself, sending ripples through space-time that might someday be detectable with observatories like LISA, the Laser Interferometer Space Antenna. Unlike ground-based detectors that catch the final seconds of stellar mass black hole mergers, LISA could sense supermassive binaries years or even decades before collision, tracking their orbital decay like a cosmic countdown clock. The payoff would be enormous. Watching a pair of supermassive black holes merge would test Einstein's theories under conditions no lab could ever replicate. The energy released in those final moments would outshine every star in the universe combined, warping space-time so severely that light itself might twist into knots. Some models suggest the merged black hole could even get kicked clear of its host galaxy by the recoil, a gravitational slingshot powerful enough to fling it into the void. Yet for all their violence, these systems might be surprisingly common. Galaxies grow by colliding, and when they do, their central black holes should eventually find each other. The mystery is why we don't see more obvious candidates. Maybe they're shy, hiding behind thick veils of dust, or stuck in a gravitational stalemate where they circle for billions of years before finally merging. Or perhaps we've been looking at the wrong wavelengths, missing subtle signatures in infrared or X-rays that would betray their presence. Every new binary candidate raises more questions than answers. Do their accretion disks tear apart as they spiral closer? Could magnetic fields between them ignite colossal explosions we've yet to imagine? And what happens to the surrounding galaxy when two gravitational monsters become one? The answers are written in the warped light of quasars, and soon, perhaps, in the faint ripples of space-time itself. One thing's certain: when we finally catch two supermassive black holes in the act, the universe won't let it happen quietly. Quasars were never supposed to flicker like dying light bulbs. These cosmic beacons were thought to burn with relentless fury for millions of years. Yet astronomers keep catching them in the act of cosmic resurrection, fading to near darkness before roaring back to life as if someone flipped a switch. Take J1012 plus 0635, a quasar that dimmed by a factor of 50 in just 4 years, its ravenous black hole seemingly going on a diet before suddenly binge eating again. This wasn't a slow decline. It was a lights-out moment followed by a violent rebirth, and it's forcing scientists to rethink everything about how these monsters live and die. The leading suspect behind these on-off episodes is the black hole's feeding schedule. Imagine a supermassive black hole as a picky cosmic toddler. Sometimes it gorges on gas clouds, sometimes it throws its plate across the room. When a fresh stream of matter spirals inward, the quasar flares to life. When the buffet runs dry, the engine sputters. But what causes such drastic interruptions? One theory points to chaotic accretion disks, where magnetic instabilities or turbulence create feast or famine cycles. Picture a whirlpool that periodically chokes on its own chaos, leaving the central black hole momentarily starved. There's a darker possibility: orbital dynamics. Some quasars might share their space with a second black hole, an unseen dance partner whose gravity kicks the feeding disk like a bully shaking a vending machine. Every close pass could disrupt the flow of gas, causing the quasar to flicker in sync with their orbital period. We might be watching cosmic tag team wrestling, where one black hole's movements dictate when the other gets to eat. Yet the weirdest cases defy even these explanations. Take SDSJ0159+0025, a quasar that vanished entirely twice before reappearing decades later. No gradual dimming, no warning, just a celestial game of peekaboo. Some astronomers argue these extreme cases could involve rogue stars or gas clouds passing directly between us and the quasar, acting like a cosmic eclipse. But that requires near-perfect alignment across billions of light years, a coincidence so unlikely it borders on absurd. The stakes are higher than just solving a puzzle. If quasars commonly cycle through rebirths, it means entire galaxies might experience periodic bursts of violent energy, enough to sterilize budding star systems or kickstart new ones. These aren't just black hole tantrums, they're cosmic climate change events written in light. And with next-gen telescopes scanning deeper into space, we're about to find out just how often the universe hits the reset button on its most luminous monsters. Light doesn't always travel in straight lines, at least not when it's escaping a quasar. Some of these cosmic monsters shoot beams of light so twisted that they resemble the glare off a freshly waxed car, their waves aligned in bizarre, unnatural patterns. This polarized light isn't just a curiosity, it's a secret message from the heart of the storm, revealing forces at work that we can't see directly. And just like polarized sunglasses cut through reflections to unveil hidden details, astronomers use this quirk of light to peer past the chaos and decode what's really happening near these black holes. The mystery begins with how polarization happens. Normally, light waves vibrate in all directions as they travel, like a jump rope being shaken randomly. But when light passes through certain environments, say, a cloud of magnetized gas or the edge of a swirling accretion disk, those waves get funneled into a single plane, like the rope now being swung strictly side to side. Quasars take this to extremes, with some emitting light up to 20% polarized, a sign that something violent is organizing those photons on their way out. One explanation points to magnetic fields strong enough to bend spacetime itself. Picture the quasar's core wrapped in coils of magnetic energy, twisting so tightly they act like a cosmic prism, filtering and aligning the escaping light. These fields might arise from the accretion disk's insane rotation, spinning faster than a blender on its highest setting until magnetism becomes the dominant force. The result, light that's not just bright but structured, carrying an imprint of the forces that shaped it. Then there's the obscuration theory. Some quasars might be partially hidden behind thick donuts of dust structures called toriae that scatter their light like fog, diffusing a lighthouse beam. As photons squeeze through these choked corridors, only those vibrating in certain directions make it through, creating polarized patterns. It's the difference between seeing a street lamp clearly and glimpsing one through a frosted window. The distortion tells us about the obstacle itself. But the real surprises come when polarization changes. A few quasars flip their polarization angles over weeks or months, as if their magnetic fields are thrashing like snakes in a sack. This could mean the disk is wobbling, or worse, that the black hole's spin axis is tilted compared to its accretion disk, creating a cosmic gyroscope effect that warps everything around it. The stakes are higher than just solving a puzzle. Polarized light might hold the key to one of Quasar's biggest mysteries: how they launch their jets. Those narrow, high-speed beams could be guided by magnetic fields acting like cosmic railguns, and polarization gives us a way to trace their blueprint. Every twisted photon is a clue, a breadcrumb leading back to the engine room of the universe's most powerful dynamos. So next time you put on polarized sunglasses to cut through glare, remember astronomers are doing the same thing, just on a scale that spans galaxies. The universe is full of hidden messages written in light, and quasars, they're practically screaming theirs in neon. Quasars are supposed to follow cosmic recipe books. Their light should reveal the same familiar mix of hydrogen, helium, and heavier elements we see throughout the universe. But every now and then, astronomers catch one that breaks the mold, flaunting chemistry so bizarre it's like finding a gourmet dish in a fast food menu. Take the quasar APM 08279 plus 5255, whose spectrum screams with iron levels 10 times higher than normal. It's as if someone took a cosmic magnifying glass to the universe's forge, supercharging the creation of heavy elements in ways we've never seen before. What makes these oddballs even stranger is that they're not just overstuffed with one element, they're often missing key ingredients too. Some quasars show shockingly low levels of carbon or oxygen, elements that should be abundant in any stellar kitchen. It's like a cake recipe that calls for buckets of salt but skips the flour entirely. One leading theory suggests these anomalies might be fossils from the universe's earliest epochs, when the first generations of stars, called population 3 stars, cooked elements in fundamentally different ways. These pioneers would have been massive, short-lived giants, fusing hydrogen and helium into heavier elements at breakneck speeds before exploding in hyper-nova so violent they could have seeded quasars with exotic chemistries. But there's a twist. Other weirdly metal-rich quasars might be showing us something even wilder: entire galaxies that evolved on fast-forward. In dense cosmic environments, star formation can go into overdrive, producing supernova at rates so frantic they flood surrounding gas with abnormal amounts of iron and nickel. Over time, this polluted gas falls into the central black hole, imprinting its unusual signature on the quasar's light. Imagine a city where fireworks factories keep exploding. Eventually, the air would be thick with gunpowder residue. That's essentially what we might be seeing in these overachieving galaxies. Then there's the dark horse explanation. Some quasars could be feeding on the remains of rare stellar oddities. Neutron star collisions, for instance, are famous for spewing out gold and platinum. Could they also dump enough strange metals into a black hole's diet to alter its emission line? Or perhaps these quasars are guzzling gas from ancient, metal-rich planets or asteroids torn apart by tidal forces. It's a cosmic buffet where the rarest dishes leave the strongest aftertaste. The implications stretch beyond curiosity. If these chemical outliers trace back to primordial stars, they're time capsules from an era before Earth even existed. But if they're products of extreme environments, they could rewrite how we model galaxy evolution. Every anomalous emission line is a clue, a breadcrumb leading us through the universe's most unconventional kitchens, and proving that even in the vastness of space, the rulebook is always up for revision. Quasars come in 2 flavors. Some blast the cosmos with radio waves like a cosmic air horn, while others whisper in silence. This split between radio loud and radio quiet quasars has baffled astronomers for decades because at their core, both types are powered by the same violent engine, a supermassive black hole devouring matter at a staggering rate. So why do some launch jets screaming across the universe, while others seem content to glow without the pyrotechnics? The answer might rewrite how we understand these monsters' diets and personalities. Radio-loud quasars are the showboats of the cosmos. Their jets, twin beams of charged particles racing near light speed, can stretch millions of light years, plowing through intergalactic space like superheated bulldozers. These aren't gentle streams, they're particle accelerators on a galactic scale, twisting magnetic fields into knots and glowing bright in radio frequencies. Cygnus A is the poster child here, its jets carving colossal bubbles of radiation into the cosmos. But radio-quiet quasars, despite having black holes just as massive and active, act like someone muted their speakers. Their light is just as brilliant, but the radio silence suggests their energy bleeds away more subtly, perhaps as heat or ultraviolet radiation rather than high-velocity cannon fire. One leading theory points to the black hole's spin. Picture a figure skater pulling their arms in to rotate faster. Black holes do the same with infalling gas. A high-spin black hole might wind magnetic field lines into a tight coil, launching focused jets like a cosmic railgun. Meanwhile, slower spinning monsters could churn their surroundings more chaotically, dissipating energy as diffuse heat rather than structured beams. Supporting this, some radio-loud quasars show evidence of faster spins, though the data isn't unanimous. Then there's the environment argument. Maybe radio-quiet quasars live in gas-poor neighborhoods where the black hole's meal arrives in dribs and drabs, preventing the formation of stable jets. Think of it like the difference between a well-stoked bonfire and a sputtering campfire. Both burn, but only one roars. Observations of host galaxies back this up. Many radio-loud quasars sit in galaxy clusters with plenty of fuel, while their quieter cousins often drift in isolation. But the wild card is magnetic fields. Some models suggest jet formation depends less on spin or food supply, and more on how orderly the black hole's magnetic plumbing is. If field lines are tangled like spaghetti, energy leaks out in all directions. But if they're neatly aligned, like strands of a harp, they can channel particles into tight, screaming jets. This might explain why even some well-fed, fast-spinning quasars stay radio-quiet. Their magnetic fields could be too messy to focus the energy. The truth might be a mix of all three. Just as a car's performance depends on engine power, fuel quality, and mechanical tuning, a quasar's radio voice could hinge on spin, environment, and magnetic alignment working in concert. And with new telescopes mapping black hole magnetic fields in unprecedented detail, we're closer than ever to hearing the full story behind these cosmic roars and silences. Because in the end, whether a quasar shouts or whispers, it's still telling us how the universe's most powerful engines tick. Gravity doesn't just trap light, it can bend it into a cosmic magnifying glass, and quasars are some of the universe's most powerful lenses. When one of these brilliant beacons aligns perfectly with a distant galaxy behind it, something extraordinary happens. The quasar's immense gravity warps space-time so severely that the background galaxy's light gets stretched, duplicated, and amplified into multiple images. The result, a natural telescope crafted by the universe itself, giving us front-row seats to galaxies otherwise too faint to see. Take the Einstein cross, one of the most striking examples. Here, a quasar 400 million light-years away acts like a prism for a galaxy 10 times farther back, splitting its light into 4 perfect copies arranged in a cross pattern around the quasar. Each image is the same galaxy, its light taking slightly different paths around the gravitational well like cars navigating a roundabout. This isn't just a pretty illusion, it's a goldmine for cosmologists. By measuring the time delays between the images, some arrive days or weeks apart due to their varied routes, scientists can calculate the universe's expansion rate with pinpoint precision. But the real magic happens when lensed quasars reveal the invisible. The amount of distortion in the background galaxy's light betrays the mass of everything along its path, including dark matter. In some cases, the lensing effect is so pronounced that it stretches the galaxy into a luminous arc, a smear of starlight wrapped around the quasar like a halo. These Einstein rings are nature's way of sketching the gravitational scaffolding of the cosmos, outlining where unseen matter clumps and twists. Some quasars even pull double duty. While their own light illuminates their immediate surroundings, their lensing effect peers billions of years further back, offering a two-for-one glimpse into different epochs of the universe. Imagine holding a flashlight that not only lights up your backyard but also, somehow, illuminates a distant mountain range behind it. That's the power of gravitational lensing. The most mind-bending part, these cosmic magnifiers are self-correcting. As galaxies and quasars drift through space, their alignments shift, offering fresh viewpoints over time. A quasar that's silent today might lens a spectacular background galaxy tomorrow, proving the universe always keeps a few extra tricks up its sleeve. So the next time you hear about a lensed quasar, remember, you're not just looking at a distant object. You're seeing the universe's own artistry, painted with the brushstrokes of gravity itself. Galactic collisions are the ultimate cosmic demolition derby, giant islands of stars smashing together with such force that they can awaken sleeping monsters. At the heart of most galaxies, supermassive black holes lie dormant, starved of fuel. But when two galaxies collide, the chaos that follows is like throwing gasoline on a smoldering fire. Vast rivers of gas, once peacefully orbiting in separate systems, get funneled toward the merged galaxy's center in a gravitational free-for-all. The result? A quasar is born, its hunger suddenly satisfied by an all-you-can-eat buffet of interstellar material. Hubble has captured these violent births in stunning detail. One iconic image shows the Tadpole Galaxy, its long tail of stars stretched like taffy by a recent collision, and right at its heart, a newly ignited quasar blazing to life. Simulations reveal even more. When galaxies spiral into each other, their gas clouds don't just drift inward politely. They crash, compress, and ignite bursts of star formation, while a portion gets diverted straight into the black hole's maw. It's like two hurricanes merging, with all that churning energy focused into a single, catastrophic vortex. What's fascinating is the timeline. These feeding frenzies don't happen overnight. After the initial collision, it can take millions of years for gas to finally reach the center, meaning the quasar's eruption is a delayed cosmic firework. Some models suggest the brightest quasars might even require multiple mergers, a series of galactic pile-ups that keep topping up the black hole's fuel reserves. But here's the twist: not all galactic collisions create quasars. The outcome depends on the gas supply. Two spiral galaxies rich in star-forming fuel. Perfect quasar recipe: two elliptical galaxies already gas-starved, more of a fizzle than a bang. It's like trying to start a campfire with wet wood versus dry kindling. And sometimes the collision can be too violent, the gas gets blown away entirely, leaving the black hole high and dry. The aftermath is just as dramatic. As the quasar feasts, its radiation and outflows heat up or expel the remaining gas, effectively shutting off future star formation. It's a self-destruct mechanism. The same collision that ignited the quasar eventually starves it, leaving behind a quieter elliptical galaxy. A cosmic rise and fall written in light and gravity. These cataclysms aren't just ancient history either. Right now, in a galaxy far away, two spirals might be tangling in a gravitational dance, unaware that their fate and the birth of a new quasar is already written in the stars. Most cosmic jets fire straight as laser beams, but some quasars whip their particle streams around like wild fire hoses, knotting, wobbling, and even flipping directions entirely. These unstable jets defy the laws of orderly physics, dancing to a chaotic rhythm that shouldn't exist near a black hole's precise gravitational grip. Take Blazar Markarian 501, whose jet famously twisted 40 degrees in just 2 years, the cosmic equivalent of a freight train switching tracks at full speed. What could possibly yank a jet packing the energy of 1 trillion suns off course? One compelling culprit hides in the black hole itself: precession. Picture a spinning top wobbling as it slows. That's precession in action. Now scale it up to a black hole spinning off kilter relative to its accretion disk. The resulting gravitational torques might warp the entire system, causing the jet's launch axis to slowly trace circles in space like a wobbling lighthouse beam. Some models even suggest binary black holes could exacerbate this effect, their orbital motion adding extra tugs to the jet's trajectory. But precession alone can't explain the most violent swerves. That's where clumpy accretion disks enter the scene. Normally, gas spirals inward smoothly, like water draining down a tub. But turbulence or magnetic instabilities can shred this flow into dense chunks. Think of boulders tumbling down a river instead of sand. When these massive clumps plunge toward the black hole, their asymmetrical gravity might jerk the jet sideways like a puppeteer yanking strings. Radio observations of knotty jets support this. Bright blobs often coincide with sudden direction changes, as if each new gas globule delivers a fresh kick to the particle beam. The most extreme cases might involve full-scale disk ruptures. Simulations show that if a passing star or gas cloud gets torn apart near the black hole, its debris can slam into the disk like a cannonball, temporarily hijacking the jet's path. These chaotic meals could explain why some quasars' jets flicker erratically between stable and unstable states. They're not just wobbling but being yanked around by cosmic food fights in progress. Yet the weirdest twist comes from relativity itself. Near a rapidly spinning black hole, frame-dragging warps spacetime so severely that magnetic field lines which guide jets get twisted like spaghetti. If the spin axis tilts even slightly over time, these contorted fields might violently snap back into new alignments, whipping the jet in unpredictable directions. It's the ultimate cosmic whiplash, where gravity's own rules force jets into shapes no engineer could design. Every misbehaving jet forces astronomers to ask, are we seeing chaos or precision? What looks like instability might actually be a finely tuned system responding to forces we've yet to map. One thing's certain: when a jet starts dancing, it's not just putting on a show. It's revealing the invisible forces shaping the darkest corners of the universe. The early universe wasn't supposed to have monsters. According to everything we know about cosmic evolution, the first galaxies should have been modest things, small, fragile nurseries where stars flickered to life in slow motion. But the universe loves a good plot twist. Astronomers have now spotted quasars blazing less than 700 million years after the Big Bang. They're supermassive black holes already weighing in at billions of solar masses. That's like finding a skyscraper in the middle of the Stone Age, an impossibility that's forcing us to scrap the rulebook on how galaxies grow. Take Quasar J0348 plus 0032, one of the earliest known. Its light spent 12.9 billion years racing toward us, meaning we're seeing it as it was when the universe was barely out of diapers. Yet this cosmic toddler already hosts a black hole over 1 billion times heavier than our Sun. The math is brutal. Even if this black hole ate at the theoretical maximum rate, gobbling gas non-stop, 24/7, it shouldn't have had enough time to bulk up to this size. It's the equivalent of a baby gaining 200 pounds in a week. Something's missing from the equation. One radical idea: these black holes might have skipped the appetizers and jumped straight to the main course. Instead of growing slowly by nibbling on gas clouds, they could have formed from direct collapse seeds, enormous clumps of primordial gas that collapsed straight into black holes thousands of times heavier than the stellar mass variety. Picture a cloud so dense and cold that it bypasses star formation entirely, imploding under its own weight like a house of cards in a hurricane. These cosmic shortcuts would give quasars a head start, allowing them to pack on weight faster than standard models allow. The problem: we've never actually spotted one of these direct collapse black holes in the wild. They'd need pristine gas unpolluted by heavier elements, conditions that might have existed only in the universe's first 100 million years. Some theorists argue we're looking for ghosts. Others counter that we just haven't pointed our telescopes at the right patch of sky yet. Then there's the merger theory. Early galaxies might have been like piranhas in a feeding frenzy, constantly colliding and merging in a chaotic young cosmos. Each smash-up would funnel fresh gas to the central black hole, creating bursts of hypergrowth. Simulations show that in dense protoclusters, black holes could have gained mass 10 times faster than we thought possible, like contestants in a cosmic eating contest with no rules. But the biggest headache comes from the quasars themselves. Many show heavy elements like iron in their spectra, elements that shouldn't exist in meaningful quantities until generations of stars had lived and died. It's as if these black holes didn't just grow fast, their entire galaxies industrialized at warp speed, churning out stars and supernova at rates that defy modern analogs. Maybe the early universe was a place of extremes where everything, star formation, black hole growth, chemical enrichment, ran on overdrive. The James Webb Space Telescope is now hunting for answers, peering deeper into the cosmic dawn than ever before. Every new ultra-distant quasar it finds is a time capsule, preserving clues about an era when the rules were different, or perhaps when we simply haven't learned them yet. One thing's certain: the early universe wasn't playing fair, and that's what makes it so thrilling. Quasars are cosmic beacons that should shine brightly across all wavelengths, especially in the ultraviolet range, where their scorching accretion disks pump out staggering amounts of energy. Yet astronomers keep stumbling upon bizarre outliers that defy expectation. Quasars with UV light that's suspiciously absent, like bonfires missing their flames. These enigmatic objects don't just puzzle scientists, they threaten to upend how we measure the vast distances of the cosmos. The mystery begins with dust. One leading theory suggests these quasars might be shrouded in thick cocoons of cosmic soot, dense clouds of carbon and silicate grains swirling close to the accretion disk. UV light, being short wavelength and energetic, gets absorbed more easily by dust than longer wavelength radiation. It's like trying to see a flashlight through thick fog. The beam might still be there, but it's effectively invisible to our telescopes. Some of these quasars even show reddened spectra, their light skewed toward redder wavelengths, just as sunlight appears redder at sunset when filtering through Earth's atmosphere. But dust alone can't explain the most extreme cases. Take quasar SDSSJ 0120 plus 0065, whose UV deficit is so severe it's as if someone snipped an entire chunk of its spectrum. Here, researchers suspect a more exotic culprit, an accretion disk running in hard state. Normally, a disk glows like a blackbody radiator, emitting smoothly across wavelengths. But under certain conditions, like when the black hole is feeding unusually slowly, the disk might transition to a state where it emits mostly X-rays instead of UV, leaving an eerie gap in its light signature. Imagine a stove that only gets hot enough to sear steaks but never boil water. It's still cooking, just in an unexpected way. The stakes skyrocket when we realize how much cosmologists rely on quasars as yardsticks. For decades, the UV brightness of quasars has been a key tool for estimating cosmic distances, particularly in the early universe. Astronomers use a method called the UV-X relation, which links a quasar's UV and X-ray emissions to its intrinsic luminosity. But if some quasars are missing their UV light, whether from dust, odd accretion modes, or something else entirely, these measurements could be catastrophically off. It's like trying to navigate by lighthouses only to discover some have dimmed their beams without warning. And there's a wilder twist. What if the missing UV isn't missing at all, but shifted? Some theorists propose that in extremely high redshift quasars, the UV light could be stretched so far into the infrared by the expansion of the universe that our telescopes misclassify it entirely. Others wonder if magnetic fields might be playfully distorting the light's path, like a funhouse mirror bending reflections in unexpected directions. Every UV-deficient quasar forces astronomers to ask uncomfortable questions. How many have we misjudged? Are our maps of the cosmos subtly warped by these cosmic illusions? The answers might not just solve a quasar puzzle, they could rewrite how we see the universe's grand structure. And that's the real shock. Sometimes what's absent tells us far more than what's there. Gamma rays are the universe's most violent fireworks, bursts of energy so intense they can outshine entire galaxies in a single heartbeat. And while we often associate these explosions with colliding neutron stars or supernova, some of the most extreme gamma ray flares come from an unexpected source: quasars. Not all quasars unleash this level of mayhem, but when they do, it's like watching a cosmic volcano erupt without warning. The Fermi Gamma Ray Space Telescope has caught these monsters in the act, recording flares so powerful they momentarily drown out every other source of gamma rays in the sky. What makes these outbursts so bizarre is their sheer unpredictability. Unlike the steady glow of a quasar's accretion disk, gamma ray flares spike suddenly, sometimes doubling the quasar's brightness in just hours before vanishing just as fast. Take the Blazar 3C279, which in 2019 shot out a gamma-ray flare packing 5 times its usual energy output, an event so bright it briefly became the most luminous object ever observed in gamma rays. The leading suspect: catastrophic collisions within the quasar's own jets. Picture a highway where streams of particles race near light speed, and suddenly 2 high-speed cars smash together. The resulting pileup would unleash a shockwave of gamma radiation visible across the universe, but jets aren't the only agitators. Some flares might stem from the black hole's dining habits. If a particularly large gas cloud or even a star strays too close, the black hole's tidal forces can shred it apart in a matter of hours. As the debris spirals inward at relativistic speeds, friction heats it to billions of degrees, sparking a gamma-ray firestorm. Fermi has spotted quasars flaring right after suspected tidal disruption events, as if the black hole is belching out the remains of its meal in a burst of high-energy indigestion. The real challenge is catching these flares in action. Gamma rays don't penetrate Earth's atmosphere, so Fermi orbits above it, scanning the skies for sudden spikes. When it detects one, astronomers worldwide scramble to point other telescopes, X-ray, optical, radio, at the culprit, hoping to catch the aftermath from multiple angles. It's like trying to photograph lightning by listening for thunder. By the time other instruments look, the brightest flash may already be fading. Yet these fleeting outbursts are more than just cosmic spectacles. They're probes into the most hostile environments near black holes. The gamma rays' energy and timing reveal details about jet structures and magnetic fields that would otherwise stay hidden. Some flares even show subtle flickering, hinting at processes happening alarmingly close to the event horizon, where space-time itself is fraying at the edges. So next time Fermi alerts astronomers to a gamma-ray flare, remember, it's not just a distant explosion. It's a message from the edge of oblivion, written in the universe's most extreme language. And decoding it might just teach us how black holes bend the rules of physics to their will. Quasars burn with such ferocious brilliance that astronomers once dreamed of using them as cosmic mile markers, lighthouses, to map the farthest reaches of the universe. After all, if their light can cross billions of years to reach us, shouldn't their brightness reveal how far they've traveled? The idea is seductive. A universal standard candle that could measure distances deeper into space than even the brightest supernova. But quasars, true to form, refuse to play by the rules. Their wild variability and enigmatic physics make them the trickiest distance markers imaginable, a cosmic ruler with a mind of its own. The first hurdle is their sheer unpredictability. Unlike Type 1, a supernova which explode with near-identical brightness, quasars flicker like candle flames in a storm. One might blaze 10 times brighter than another with the same redshift, not because it's farther or closer, but because its black hole happened to gulp down a gas cloud that day. Imagine trying to judge distances by street lamps that randomly dim and surge. You'd never trust your map. This volatility stems from their feeding habits. A quasar's luminosity depends on how much gas its black hole is devouring, and that menu changes by the hour. Then there's the UVX problem. Astronomers noticed a curious pattern. The brighter a quasar's ultraviolet glow, the stronger its X-ray emissions. This correlation seemed promising, a potential ruler to gauge intrinsic brightness. But further observations revealed cracks in the theory. Some quasars flout the UVX relationship entirely, their X-rays mysteriously weak or missing. Others show shifts over time, as if the connection between their emissions is a fraying rope. The culprit, hidden dust clouds, might be absorbing UV, or magnetic fields could be diverting energy away from X-rays. It's like trying to measure a car's speed by its engine noise, only to realize some vehicles have broken mufflers. The final nail in the coffin comes from geometry. Supernova explode in roughly spherical bursts, so their brightness dims predictably with distance. But quasars beam much of their radiation in narrow jets, meaning their apparent brightness depends wildly on whether we're staring down the barrel or seeing them from the side. A jet pointed straight at us might look thousands of times brighter than the same quasar viewed edge-on, a cosmic version of getting flashlight blinded because someone aimed it at your eyes. Even worse, some quasars seem to change their angle over time, twisting the illusion further. Yet hope isn't entirely lost. Recent studies suggest certain subtypes, like ultra-luminous quasars in pristine gas clouds, might follow tighter brightness rules. Others propose using machine learning to untangle the chaos, training algorithms on thousands of quasars to spot hidden patterns in their variability. It's a long shot, but in a universe where quasars already defy every expectation, maybe their greatest rebellion will be becoming reliable after all. Until then, they'll remain the cosmos' most dazzling enigmas, brilliant enough to guide us but too wild to trust. Some quasars don't just shine, they sing. In a cosmic version of echolocation, certain active galaxies emit light that bounces off their own swirling gas, creating delayed echoes in their spectra. These reverberating signals, known as broad emission lines, aren't just beautiful quirks, they're precise tools, allowing astronomers to measure the vast distances around supermassive black holes with shocking accuracy. It's like tapping a hammer in a cavern and timing how long it takes the echo to return, except here, the cavern is light years wide, and the hammer is the quasar's own furious glare. Here's how it works. When UV light from the quasar's accretion disk flares up, it floods nearby gas clouds with radiation, causing them to fluoresce at specific wavelengths. But because these clouds orbit at different distances, their responses aren't instantaneous. The closer clouds light up almost immediately, while those farther out reply with a delay, sometimes weeks or even months later. By tracking these staggered responses, astronomers can map the geometry of the entire system, down to the light-day or light-week scale. The result, a 3D ultrasound of a black hole's feeding zone, revealing structures no telescope could ever resolve directly. The comparison to sonar isn't just poetic, it's functionally identical. Just as submarines ping sound waves to gauge underwater terrain, quasars ping space with light, and the echoes sketch their hidden topography. Take the Seyfert galaxy NGC 5548, where reverberation mapping revealed gas clouds whipping around the central black hole at over 5,000 kilometers per second. The time delays between the disk's UV flare and the gas cloud's response showed these structures were nearly a light month away from the black hole. a distance that would swallow our entire solar system with room to spare. But the real power of this technique lies in its precision. Traditional methods of estimating black hole masses rely on assumptions about gas motion. Reverberation mapping cuts through the guesswork, delivering direct measurements based on hard physics. If a cloud's response is delayed by 20 days, we know it's 20 light days from the core. Combine that with the velocity of the orbiting gas measured by how much the emission lines are Doppler shifted, and you've got all the ingredients for a black hole's way in: distance, speed, and gravity's grip. The surprises don't stop there. Some quasars show lopsided echoes where one side of the accretion disk lights up faster than the other. This could mean the disk itself is warped, or worse, that the black hole's spin is yanking space-time into a twisted funnel, dragging nearby gas along for the ride. Others exhibit echoes that flicker unpredictably, hinting at chaotic turbulence or even hidden companions stirring up the gas. What's truly wild is that we're seeing these echoes in real-time cosmic history. The light from a quasar 8 billion light-years away shows us echoes that actually happened 8 billion years ago, yet we're decoding them now as if they were fresh signals. It's the ultimate time machine, turning quasars into celestial metronomes, their rhythmic pulses ticking off the seconds of the universe's grandest clocks. So the next time you hear an echo in a canyon, remember, the cosmos has been doing the same thing for billions of years. Only instead of sound, it uses light, and instead of rock walls, the backdrop is the infinite void itself. And every echo we catch is another piece of the puzzle, revealing how the universe's most monstrous engines are built. Hidden deep in the cosmic backwaters, strange galaxies glow with a sullen crimson hue, their gas stirred not by the fires of newborn stars, but by the restless fury of quasars at their cores. Astronomers call them red geysers, and they defy everything we thought we knew about galactic life cycles. Unlike typical galaxies where young blue stars dominate, these rusty-hued realms are eerily quiet, their star factories shuttered despite brimming with raw materials. The culprit, colossal winds blasting from their central quasars, powerful enough to scour entire galaxies clean of star-forming fuel. The mystery lies in whether these quasar-driven gales are executioners or mere bystanders. On one side of the debate, evidence suggests these outflows act like cosmic blowtorches, superheating interstellar gas to millions of degrees until it's too turbulent to collapse into stars. Picture a hurricane ripping through a cloud of flour. No matter how much raw material exists, it'll never settle into dough. Galaxies like NGC 1266 showcase this brutally. Their quasar winds have evacuated vast bubbles in the surrounding gas, leaving behind ghostly cavities where stellar nurseries should thrive. But dissenting voices argue correlation isn't causation. Maybe the quasar's fury is just the death rattle of a galaxy already doomed by other means. Some red geysers show signs of prior collisions or tidal stripping, events that could have already depleted their star-forming reserves long before the quasar woke up. In these cases, the AGN winds might be more like a feverish symptom than the disease itself, a final spectacle as the galaxy fades into retirement. The smoking gun might lie in timing. Recent observations of red geyser galaxies reveal their quasar winds often coincide with abrupt drops in star formation rates, like a cosmic circuit breaker flipping off. Radio telescopes have even caught some quasars in the act, their jets drilling through cold gas clouds and ionizing them before stars can ignite. It's a ruthless efficiency. One quasar's outburst can sterilize a galaxy for billions of years. Yet exceptions abound. A handful of red geysers still cling to patches of star formation along their outskirts, as if the quasar's reach has limits. Others show winds too weak to explain their galactic dormancy, hinting at hidden factors like dark matter halos stabilizing the gas against collapse. The truth might be messier than any theory, a feedback loop where quasars, galaxy mergers, and internal dynamics all conspire to quiet the stellar chorus. What's undeniable is how these systems rewrite galactic evolution. If quasars can indeed flick the off switch on star birth, they're not just luminous monsters, they're cosmic puppet masters governing the life and death of galaxies with their tantrums. And in a universe where stars are the ultimate currency, that makes them the most powerful bankers of all. Even the hungriest black holes don't always dine on gas, sometimes they snack on stars. When a doomed sun wanders too close to a supermassive black hole, the resulting carnage is anything but subtle. Gravitational tides stretch the star like taffy, shredding it in a cataclysm called a tidal disruption event, or TD. Normally, these flare up in otherwise quiet galaxies but catch one near an already active quasar, and the cosmic fireworks reach another level entirely. The quasar's existing accretion disk gets a sudden infusion of stellar debris, sparking a secondary eruption so bright it can momentarily outshine the entire system. These hybrid outbursts rewrite the rules of black hole meals. While steady accretion feeds quasars like a slow drip of syrup, TDs are the equivalent of pouring gasoline on a fire. Take Assassin 15LH, a quasar that briefly flared 100 times brighter after devouring a star. Its light curve spiked like an EKG during a heart attack, sharp peaks from chunks of stellar material slamming into the disk at relativistic speeds, followed by eerie plateaus as the black hole digested each course. Unlike the smooth glow of gas accretion, TD flares are messy, unpredictable feasts, their flickers betraying the violence of the process. What makes these events even wilder is their aftermath. A star's destruction doesn't just dump fuel onto the disk, it destabilizes it. Simulations show streams of stellar debris wrapping around the black hole in chaotic tendrils, some colliding with themselves in superheated shocks. The resulting turbulence can warp magnetic fields, twist jets into new directions, and even trigger secondary eruptions months later as leftover debris finally spirals in. It's like tossing a grenade into a whirlpool and watching the splash ricochet. Yet not all quasar TDs are created equal. Some, like the event in galaxy F0-100-42237, blaze with shocking amounts of X-rays, evidence that the star was swallowed whole before fully disrupting, its material compressed into a superhot plume. Others, like PS110J1809, flare mostly in ultraviolet, suggesting the debris formed a wide, glowing arc around the black hole rather than a neat disk. Each light signature tells a different story of stellar annihilation, revealing whether the star was fluffy or dense, whether it approached head-on or at a grazing angle. The rarest cases might rewrite physics itself. In 2021, astronomers spotted a quasar's TD flare that seemed to eject material faster than light, an illusion caused by relativistic beaming, where jets point nearly straight at us and warp our perception of speed. Another event in galaxy OJ287 showed bizarre oscillations in its light curve, as if the black hole was hiccuping on partially digested stellar chunks. Every time a quasar lights up from snacking on a star, it's more than just a spectacle, it's a masterclass in extreme gravity. These flares lay bare the forces tearing apart worlds, the physics of matter on the brink, and the appetites of the universe's most relentless monsters. And with telescopes scanning wider than ever, we're bound to catch more of these cosmic lunch breaks in action, each one a reminder that even giants get hungry. Among the countless quasars dotting the cosmos, a rare few defy the odds in an unsettling way. Their black holes spin in eerie unison, as if choreographed by some unseen cosmic hand. Take the Quasar Quartet, huge large quasar group, 4 active galaxies separated by billions of light years, yet their jets all point within 30 degrees of one another. The chance of such alignment happening randomly is like flipping a coin 100 times and landing heads every single time. This isn't just coincidence, it's a cosmic conundrum begging for an explanation. One tantalizing possibility lies in the fabric of the universe itself. Colossal magnetic fields stretching across filaments of the cosmic web, could act like invisible train tracks, guiding the rotation of supermassive black holes during their formation. Picture a vast river of magnetized gas flowing along these intergalactic highways. Black holes born within it might inherit its directional pull, like twigs aligning in a current. Simulations show that under the right conditions, these fields could steer spinning black holes into harmony over billions of years, their accretion disks and jets eventually locking into parallel orientations. Yet there's a catch: magnetic fields weaken over distance, and the scales involved here are staggering. Alignments spanning hundreds of millions of light years would require forces beyond anything we've directly observed. That's where large-scale structure comes in. The universe isn't random galaxies cluster along sprawling filaments with vast voids between them. Some theorists argue that during the universe's infancy, these primordial tendrils spun like cosmic whirlpools, imparting a preferred rotation direction to all the black holes forming within them. It's as if the early universe was a giant mixing bowl and everything inside got stirred the same way. But skeptics aren't convinced. They point to alternative explanations, like selection bias, where we only notice aligned quasars because their jets happen to point toward Earth, making them appear artificially synchronized. Others suggest that black holes might simply prefer certain spin axes based on how they feed. If gas flows into them along predictable paths, like water spiraling down a drain, their spins could naturally converge without any grand cosmic influence. The most mind-bending hypothesis: these alignments might be relics of the universe's birth. Quantum fluctuations in the early cosmos could have imprinted a preferred direction on spacetime itself, a faint fingerprint still visible in the spin of black holes today. If true, studying these aligned quasars would be like uncovering the universe's hidden blueprints, a glimpse into the conditions moments after the Big Bang. Whatever the answer, one thing's clear: when black holes dance in unison across the void, they're not just breaking the rules, they're revealing a deeper order to the chaos. And that's a mystery worth chasing to the edge of the observable universe. Some of the universe's most powerful engines don't blaze in visible light, they smolder in the dark. Astronomers have uncovered a cryptic class of quasars so shrouded in dust that their brilliance gets converted into a dull infrared glow, like a spotlight shining through a blanket. These dark quasars challenge our basic assumptions about how these monsters live and evolve, forcing us to ask: are they just regular quasars wearing cosmic disguises, or something entirely stranger waiting in the shadows? Take WISE J22480 3.8 plus 54215 8.5, a mouthful of a name for an even more jaw-dropping object. From optical telescopes, it looks barely noteworthy, a faint smudge in the constellation Cepheus, but point an infrared observatory like WISE at it, and the truth erupts. This is a quasar pumping out 2 trillion times the sun's energy, almost all of it absorbed and re-radiated by a cocoon of dust thicker than a nebula. It's the cosmic equivalent of muffling a jet engine under a mountain of pillows. The power's still there, just transformed. What makes these objects so puzzling isn't just their dimness in visible light. Some appear to be buried so completely that even X-rays struggle to escape, suggesting dust clouds dense enough to cloak entire solar systems. Current theories suggest 2 possibilities, each wilder than the last. First, these might be quasars caught in a fleeting phase, perhaps early in their lives, when they're still swaddled in the gas and grit of their chaotic birth galaxies. Imagine a newborn star wrapped in its placental dust but scaled up to galactic proportions. The alternative: these dark quasars could represent a distinct population altogether, black holes that feed differently, maybe gorging on unusually dusty meals that choke their own light. There's precedent for this in local galaxies like NGC 1068, where the central black hole's radiation is so thoroughly absorbed that the surrounding dust heats up to hundreds of degrees, glowing fiercely in infrared while leaving the visible spectrum eerily quiet. The real mystery is how many of these hidden giants might be lurking undetected. For every classic quasar blazing across the electromagnetic spectrum, there could be several more cloaked in dust, their contributions to cosmic history overlooked. Infrared surveys are only now lifting the veil, revealing how much we've missed by relying on visible light alone. Some estimates suggest up to half of all supermassive black holes' growth might happen during these obscured phases, meaning we've been chronicling only the loudest, flashiest chapters of their lives while the rest unfolded in darkness. The implications ripple outward. If dark quasars are indeed a common phase, they could explain why some galaxies seem to halt star formation prematurely. Their black holes might be regulating growth not with visible outbursts but with infrared ones, heating dust until it can't collapse into stars. It's a stealthy form of cosmic feedback, invisible to our eyes but written plainly in the thermal glow. Yet for all we're learning, these dust-choked enigmas guard their secrets tightly. The James Webb Space Telescope is now peering deeper into their shrouded realms, its infrared eyes tuned to the whispers of warm dust. Every new detection is a reminder that the universe doesn't always put its monsters on display. Sometimes the most powerful forces wear the quietest disguises. And that's the true lesson of dark quasars. What we don't see shapes the cosmos just as profoundly as what we do. From their gravity-defying jets to their eerie light echoes, quasars have shattered every expectation we've thrown at them. These cosmic powerhouses violate speed limits, flicker like faulty light bulbs, and even align across billions of light years as if following some unseen cosmic choreography. They're time travelers, sending us snapshots of the universe's violent youth while simultaneously reshaping galaxies in the present. Whether it's their unpredictable feeding frenzies, their dust-choked alter egos, or their habit of snacking on stars, quasars refuse to play by the rules, and that's exactly what makes them so thrilling. Think about it, we've uncovered black holes spinning in sync like dancers, quasars flickering on and off like cosmic switches, and gamma-ray flares brighter than entire galaxies. We've watched them warp spacetime into natural telescopes, blast winds hot enough to sterilize galaxies, and even disguise themselves behind curtains of dust. And just when we think we've got them figured out, they throw us another curveball, like the quasars that vanish without a trace, or the ones lurking in galaxies that shouldn't exist yet. These aren't just quirks, they're clues. Every bizarre phenomenon is a breadcrumb leading us closer to understanding how black holes grow, how galaxies evolve, and even how the universe itself stitches together the fabric of spacetime. The wildest part, we've only scratched the surface. With telescopes like James Webb probing deeper into the cosmic dawn, who knows what other secrets these luminous monsters are hiding? So here's the real question: which quasar mystery left you speechless? Was it the jets that appear to break light speed, the quasars missing their galaxies, or the way they flicker like cosmic ghosts? Let us know in the comments, and if you're hungry for more mind-bending space phenomena, hit subscribe. The universe has plenty more surprises up its sleeve, and we're just getting started.